Welcome to This Explainer. Today, we're diving deep into the hidden mathematical world that keeps our entire digital lives secure. We're going to tackle some fundamental CompTIA security plus cryptography concepts, specifically focusing on Objective 1.4, which is all about understanding the importance of using the right cryptographic solutions. Whether you're sending an email, logging into your bank, or honestly just browsing the web, cryptography is the invisible shield protecting your data. So we're going to break down how this works from the ground up. We'll compare different encryption methods, explore how keys actually travel across networks, and demystify the real math behind the secrets.
Okay, here is our roadmap for decoding encryption today. We'll start with symmetric encryption fundamentals, move into the asymmetric dual-key solution, navigate key exchange, explore algorithms and cipher suites, compare stream versus block ciphers, and finally decode key length.
Section 1. Symmetric Encryption Fundamentals.
So, symmetric encryption. This method relies entirely on one shared secret. To encrypt a message, a secret key, which could be a number, a specific word, or just a totally random string of letters, is mathematically blended with the plain text of your message. This changes the content in a very specific way to scramble it up. Then, to unscramble or decrypt it, the recipient simply blends that exact same key back in. It's incredibly straightforward, but it comes with a major, absolutely crucial prerequisite. Both the sender and the recipient absolutely must know and possess this single secret key beforehand for any of this to work.
Over the years, the actual formulas we use for this symmetric blending have evolved dramatically. Right now, AES, or the Advanced Encryption Standard, is our modern go-to standard block cipher. It offers a fantastic balance of robust security and efficiency, operating with 128, 192, or 256-bit keys. But getting to AES was definitely a process of trial and error. For instance, you might have heard of RC4. Well, multiple vulnerabilities were discovered in RC4, rendering it completely obsolete today. Even older algorithms like Blowfish and DES, the Data Encryption Standard, they were hugely significant back in their time, but they've since been replaced. Basically, their short key lengths and inherent vulnerabilities just couldn't stand up to modern computing power.
Section 2. The Asymmetric Dual-Key Solution.
Now here's where we see the core difference in cryptographic thinking. While symmetric encryption uses one shared key, which, don't get me wrong, is incredibly fast, but exchanging that single key securely over the internet is incredibly risky. Asymmetric encryption relies on a mathematically related pair of keys. You have a public key, which you make freely available to anyone in the world who wants to send you a message. Think of the public key as essentially an open padlock. Anyone can snap it shut to encrypt a message. But the magic here is that the public key cannot unlock the message. The second key, your private key, is kept strictly secret. Only this private key can decrypt the message that the public key locked. And conversely, a message encrypted with a private key can be decrypted with a public key. It is just a stunningly elegant approach.
Because you literally never have to send your private key over the network, this dual-key method ensures that malicious actors can't easily misuse the keys. The security of the public key isn't even required because, well, by definition, it's public. This method has vastly better power in ensuring information security during transmission, which is exactly why it powers our day-to-day internet communication channels. The heavy lifting here is done by a variety of asymmetric key encryption algorithms. Some of the major names you're going to see include RSA, DSA, El-Gamal, elliptic curve techniques, and PKCS. These are the engines driving secure web traffic today.
But this does raise a really practical question, right? If public keys are meant to be shared, how do you actually find someone's public key securely, and how do you know it really belongs to them and not some imposter? The solution is the digital certificate. Used heavily in the client-server model of communication, a digital certificate is basically a highly secure digital ID card. It's a package of information that contains an organization's name, the entity that issued the certificate, email, country, and most importantly, the user or server's public key. When a client and server want to establish a secure encrypted connection, they send a query over the network. The responding party sends back a copy of their certificate. The client can then extract the public key directly from that trusted certificate to uniquely identify the holder and start encrypting messages to them.
Section 3. Navigating key exchange.
So we hit a fundamental dilemma. We know symmetric encryption is fast and super efficient. That makes it great for encrypting massive amounts of data, like video streams or big file downloads. But its main disadvantage is that all parties must exchange the key before they can actually decrypt the data. So how do you send a secret key over the open internet securely, without a malicious person intercepting it? This problem is known as key exchange, or key establishment. It's the method by which cryptographic keys are safely handed off between two parties so they can start using an algorithm. If they want to use a symmetric cipher, they have to figure out how to safely get a copy of the exact same key to each other. If they're using an asymmetric cipher, they just need to reliably exchange public keys.
Section 4. Algorithms and Cipher Suites.
An algorithm, in this context at least, is just a mathematical formula used in cryptographic processes. But one single algorithm usually isn't enough to secure a network connection. Instead, we use what's called a cipher suite. This is a specialized set of algorithms working together, typically to secure transport layer security, or TLS connections. A cipher suite brilliantly combines three distinct tools. First, a key exchange algorithm. This handles the very delicate process of safely swapping the key between two devices. Once the key is safely exchanged, the second tool kicks in, the bulk encryption algorithm. This is usually a fast, symmetric cipher used to encrypt the actual heavy data being sent. Finally, the MAC, or Message Authentication Code algorithm, provides a vital data integrity check. It ensures that the data sent wasn't somehow altered or corrupted while traveling over the network. Often these suites will also include signature and authentication algorithms to verify the server or client.
Now, there are hundreds of different cipher suites out there, combining these formulas in all sorts of different ways, and some naturally offer better security than others. The structure of how these are used is completely defined in TLS standard documents. For a long time, TLS 1.2, defined back in 2008, was the most prevalent version used by web browsers. But technology marches on, and in 2018, TLS 1.3 was finalized and officially published. TLS 1.3 brought major benefits, primarily vastly improved security and noticeably faster speeds. It's really important to note that this update was strict, meaning cipher suites defined for the older TLS 1.2 generally cannot be used in TLS 1.3 and vice versa. That's because TLS 1.3 introduced some very stringent additional security requirements for its suites.
Section 5. Stream versus block ciphers.
Let's zoom back in on those symmetric bulk encryption algorithms. We have two main approaches here. First, stream ciphers. These encrypt plain text one single bit at a time, usually combining the data with a pseudo-random key stream via an XOR operation. They are lightning fast and require very little hardware complexity, but they carry a massive caveat that random starting seed must never be reused, or you risk serious security vulnerabilities. In contrast, we have block ciphers. These apply a deterministic algorithm and a fixed, unvarying transformation to large, predetermined chunks of text all at once. For example, our modern standard, AES, is a block cipher. It encrypts data in 128-bit blocks using keys of 128, 192, or 256 bits.
Section 6. Decoding key length.
You'll often hear encryption strength discussed in terms of key length, which is simply measured in bits. Ultimately, the strength of your encryption is tied directly to how difficult it is for an attacker to guess or discover your key. And this depends on both the cipher you're using and the length of the key itself. The key length determines the absolute maximum number of combinations a computer would have to guess to break the encryption algorithm through brute force. Now, short key length unequivocally means poor security. It's just way too easy for modern computers to guess. But it is vital to understand that a long key length doesn't necessarily guarantee good security automatically. The math can be perfect, but it still has to be implemented perfectly.
To truly grasp the scale of what adding bits to a key does, think about this staggering number: 3 times 10 to the 26th power. If we look at the older RC4 symmetric cipher, it supported both 40-bit keys and 128-bit keys. Now you might think 128 bits is, just roughly 3 times stronger than 40 bits, right? Wrong! Because of how binary combinations multiply exponentially, 128-bit RC4 encryption is a mind-bending 3 times 10 to the 26th power times stronger than 40-bit RC4 encryption. Adding bits to a key length scales the defensive difficulty to astronomical levels.
However, and this is a major trap for learners, you cannot simply compare key lengths across different types of ciphers. A 128-bit key in one cipher is definitely not equal to a 128-bit key in another. Here's why. Symmetric ciphers can use all possible mathematical values for a key of a given length. This gives them incredibly high strength at relatively small lengths. A 64-bit symmetric key is actually quite tough. Conversely, asymmetric public key ciphers like RSA are built on highly specific mathematical problems, like prime number factoring. Because of the nature of that math, RSA can only use a specific subset of all possible values for a key. Therefore, a 128-bit symmetric key provides vastly stronger encryption than a 128-bit RSA key. In fact, to match the cryptographic strength of a mere 64-bit symmetric key, an RSA public key cipher must use a key that is at least 512 bits long. We've covered AES, RSA, TLS cipher suites, and the mind-bending math of key links. But to wrap up this explainer, I want to leave you with this final, incredibly provocative thought directly from our source material. Many cryptographic implementations are broken before the encryption itself is broken. Think about that. Despite all this brilliant, virtually unbreakable math and keys with astronomical combinations, the underlying algorithms rarely fail us. It's almost always human error. A reused stream cipher seed, a poorly configured server, a leaked private key that brings the whole system down. It really begs the question, as our math gets stronger and stronger, are we focusing enough on the human element, which clearly remains the true weakest link in our digital security? Thank you so much for exploring the fascinating world of cryptography with me. Stay curious and keep learning.